All right, early morning here, and I guess gonna try to generate a little discussion here on ln of x. I think it's pretty important that you understand the rules of exponents, what the minus sign means, the 3 and the 2. It's going to be pretty hard to describe what's going on with the ln of x if you don't have a feeling for the exponential operations. I assume that if you're looking at this, you already know how to write the equation of exponential function from 2 points and an asymptote quickly and easily without having to go to the calculator to throw it in a regression model. So the videos are there to learn how to do that if you're not part of the class. I think it's also important that you certainly understand the relationship between exponential and logs, that they're inverses, and that a log is a command. That's a command. We've got a base, and logarithms go from quantities to exponents rather than exponent to quantity. All right, so I'm assuming that there is some understanding of this exponential logarithmic process. All right, to throw ln of 2 into the calculator, you get 0.69314. Goes on forever. We're going to replace that with 0.7. It's a little easier to work with to get a feel, just to get a feel for this calculation. And then the ln of a half is negative 0.7, the reciprocation, right? Negative exponents reciprocate bases. And all right, so we'll work with that. I think the doubling function is probably the easiest exponential model to work with. And one of the purposes of ln of x is to be able to write all the different exponential models in one language system, base E. All right, so if I want to write 3 to the x, it's approximately e to the 1.1x. They're virtually very similar. You can put them in Desmos, they're on top of each other, and they take a while to diverge. Okay, so where are we going with this? To try to get a sense of that graph, the ln of x graph. All right, and the doubling function is probably, as I say, the easiest to work with. So let's get some numbers generated. All right, if the ln, which is another way of saying log base E of, then we want everything in this parentheses to be e to the something, e to the 7th. Well, what's the exponent you put on top of e to get e to the 7? A 7. All right, so ln of 2. We need to write the ln of 2. We need to write 2 in e notation, and it turns out it's approximately e to the 0.7. So therefore, what's the exponent you put on top of e to get e to the 0.7? 0.7. Right. So what would we do to get the exponent on top of e that gets a 4? Well, we know 2 squared is 4, and we can say that 2 now is e to the 0.7. Okay, I think our rules of exponents come into play. Looks like it's 1.4. All right, is it a big step to get 8? I don't think so. I think we want to cube 2 to get 8. So 2, instead of being squared, gets cubed, and we get 2.1. I think we can stop right there and see a pattern. 2.8, 3.5, etc., etc., etc. So on the left side, a pattern, and on the right side, a pattern. But that's for e to the x. We're looking at the ln of x. And instead of exponent to quantity, we're going to be doing quantities to exponent. Boy, this is a strong marker. Woo, a lot of ink. Quantity to exponent. And I think we've got some quantities and exponents over here. And needless to say, looks like negative 1.4 is going to get us a 4th. And negative 2.1 is going to get us an 8th. And negative 2.8 is going to get us a 16th. I think we're generating a pattern. Let's get rid of this. And you want to become familiar with these table values, because we're going to practice our rules of logarithms based on these values. All right, so x ln of x. Well, what's x in this case? X in this case is this column. 1/16, 1/8, 1/4, 1/2, 1 big time number there. 2, 4, 6, up 2, 4 doubling, 8, 16. All right, so what do we have for answers here? 0, which actually is e to the 0x. We don't have any growth and decay there. No. Negative 0.7, negative 1.4, negative 2.1, negative 2.8, 0.7, 1.4, 2.1, 2.8, etc. So let's go over and graph it, see what it looks like. All righty, let's see. I don't know why I wrote that, but don't need to work with it now. I think we just covered it over there. Righty. So let's look. 0, ln of x. So the ln of 1 is 0. Put that right there. The ln of 2 is 0.7. The ln of 4 is 1.4. The ln of 8 is 2.1. And the ln of 16 is 2.8. Well, it sure looks like we keep going up by 0.7. And it looks like it takes a little bit more of a quantity each time, which appears to me to be the inverse of that branch of e to the x. Instead of going up fast, instead of my y values going up fast, they appear to be going up slowly. But I got a feeling that's going to continue forever. I got a feeling the y values are going to infinity, even though they don't look like they are. Yeah. Now, what happens in between 0 and 1? Ooh, a lot. Pretty hard to show. So let me expand upon it with a different. Yeah. So here's 1 on the x-axis. Here's your x-axis, right? And 1 gets us 0, but a half gets us negative 0.7. And a fourth gets us negative 1.4. Negative 2.1. And a 16th. It's right there. Oh, my goodness. That appears to be heading towards the y values. Appear to be heading towards, negative infinity. And it all happens in such a small section of that x-axis, but can be thought of as a big section, because I think you can do this forever. And I do think we're approaching a number. And I hope you said x equals 0. So how would we communicate that? We got to come up with a language system to communicate what's going on here, what I just did. And I did talk about the y values here, and I think we can probably write the word limit and put that into your vocabulary. Yeah, there seems to be a limit as my x values go to 0. I'm moving towards 0. Of course, I'm coming towards 0 from above, because, 0, I could come to 0 from 2 directions, and I only went from 1 direction here, from above, and it sure looks like my function is doing something. Looks like those y values, looks like the y values here, the limit, as x's go to 0 from the right of this function, negative infinity, and that's called planting a seed. Because that might be the first time you've heard of that, and you're going to hear about it a lot more. So it's good that we talk about it early on in your education so that you start to let your brain work on that one a little bit. All right, so bottom line, ln of x, x-axis, 1 is extremely important. The asymptote is extremely important. You can't see that. Okay, x equals 0, and it looks like it has that general trajectory. And what do we have on the x-axis? Quantities produced from what? Exponents. And what does a 2 get me? A 2 gets me a height of 0.7. And what is 0.7? It's the exponent I put on top of e to approximate the number 2. Why is that important? Because if I wanted to write 2 to the x, I could probably write it as e to the 0.7x and be very similar. If I want to be exact, e to the ln of 2, x ln 2, e to the x ln of 2. I'm not writing that very well, but hopefully I said it properly. Okay? And that's exactly equal to that. This is a darn good approximation. And we're going to be learning our rules of exponents. For instance, what's the ln of 6? We're going to get it organically. Well, I know that 6 is 2 times 3. I know 2 is e to the 0.7. And I've asked you to memorize what 3 is, e to the 1.1. Well, it sure looks like the exponents are being added here. 0.7 e to the 0.7 plus 1.1, running out of room, which means that I now have one rule of logarithms. ln of 2 plus ln of 3 equals ln of 6. And we will be looking at these rules in more detail right after midterm. Right now, you got enough on your plate, but again, planting a seed of what are called log rules. And I think those take a while to learn. All right, I've talked quite a bit here. And I don't want these videos to be too long because then nobody's going to watch them. And we're trying to get some thoughts into your head. So that'll do it. And hopefully I'll put this up in another day or two and give you a chance to look at it when you've got the time. All right, bye-bye.